Okay, good morning, dear students. This morning, we shall tackle two topics, polynomial sketching using derivatives and optimization. So, we hope that by next meeting, we shall begin with integral proper. Okay? So, we will try to finish everything this morning on polynomial sketching and optimization, minima, maxima, or applications of your derivative concept. So we begin with polynomial sketching. Okay, but first, let's look into the concept of relative extrema. What is relative extrema? So that if we could identify the turning points of the curve, we could easily sketch its graph with the use of derivatives by first identifying the relative extrema, minimum or maximum points or turning points, okay, even inflection points of a curve. Okay, but how do we do that? Now, let f be a function defined in the interval ab. Okay, the function f is defined at a number c. So, c is contained within that interval and such that c must be greater than a but less than b. So, it's within that interval. If f of c, okay, or rather f of c is a relative maximum. It's a relative. When is it a relative maximum? Maximum highest point, okay? Minimum lowest point. If, okay, f of c is a relative maximum if there exists an interval AB such that f of c is greater than f of x for all x in that interval. And when is it a relative minimum? F of c, the function value at c, f of c is a relative minimum if there exists an interval AB such that f of c is less than f of x for all x in AB. Okay? And it says here, number 3, if f has a relative extremum and correction, this is and f prime of c exists, then f prime of c is equal to 0. Okay? So, c is a critical number. Okay? C is a critical number. What do we mean by a critical number? You'll understand this better with an example. Let's look into the definition of a critical number. A critical number, by definition, is, okay, value at which the first derivative is equal to 0. Okay? That value of x, that will make the first derivative, okay, 0, or that in which the first derivative does not exist. Once again, the critical number is the x value at which the x value, okay, where f prime of x is equal to 0, or where f prime of x does not exist. Okay? If f prime of x is equal to 0, and when f prime of x does not exist, this is how we identify the critical number. Now, let's look at one example. Let the function be f of x. So, first step to polynomial sketching using derivatives, first thing that we have to know is critical number. How do we identify the critical numbers? Now, let's go back to the problem given. F of x is equal to x squared plus x all over x. Okay? So, let me copy f of x. What is the problem asking for? First, we identify what the critical numbers are, if there are critical numbers for this given function. F of x. So example number 1, f of x equals x squared plus 1 all over x. Now going back to the definition, okay, the value of x at which the first derivative is 0, or that value of x that does not make, or should I say, in which the first derivative does not exist. So meaning, to find the critical number, we first take the first derivative. Okay, so we differentiate the function. F prime of x equals, okay, this is a quotient, so we apply quotient rule. Denominator times derivative of the numerator, 2x, minus the numerator, x squared plus 1, times derivative of the denominator, which is 1, all over the square of the denominator. Okay? All over the square of the denominator, which when simplified gives f prime of x equal to 2x squared minus x squared minus 1. Okay? All over x squared. Then from here, simplifying it further, this one will yield x squared minus 1 over x squared. A question: what value of x will make the first derivative 0? Okay, going back to our definition of a critical number, okay, let me highlight f prime of c equal to 0, or f prime of c does not exist. So going back, looking at the first derivative of the function given, f prime of x equals x squared minus 1 over x. What x value or values will make f prime of x 0? Okay, so how do we identify those values? To find the critical numbers, we equate the first derivative to 0. Equate f prime of x to 0. Okay, let's equate it to 0. X squared minus 1 over x, this is supposed to be x squared, equal to 0. Okay, so x squared minus 1 equals 0. X squared equal to 1. And extracting the square root of 1 will end up with two values of x, positive and negative 1. Okay? So, are these the only critical numbers for the function given? Okay, are these the only critical numbers? Positive 1 and negative 1? Now, going back, look at your first derivative. What can you say about the denominator? Or is there a value of x that will make this undefined or does not exist? Is there an x value that will make this undefined? Particularly pay attention to the denominator. Take note that the denominator cannot be 0, because the moment the denominator is 0, then f prime of x is undefined, does not exist. So there is one more critical value, and that is 0. Okay? So another critical value is 0. So let me add, x is also equal to 0. X equal to 0. So how many critical numbers, not critical value, critical numbers supposed to be, critical numbers. How many critical numbers have we identified for this function? There are 3, -1, +1, and 0. How did we get 0? Okay, by definition, if f prime of c does not exist, then c is a critical number. Okay, what value of x will make this undefined? Look at the denominator. Okay, denominator cannot be 0, therefore 0 is a critical number. Okay, now let's move on to the next example. How about, okay, what about number 2? F of x is equal to x cubed. F of x is equal to x cubed minus 3x squared minus 36. Okay, find the critical numbers. Okay, find the critical numbers of the given function. Find the critical numbers, so just the same. Let me copy the given. May we have our solution here. So example number 2, problem number 2, f of x equals x cubed minus 3x squared, x cubed minus 3x squared minus 36. Okay, so what are we going to do once again? Find the first derivative. Okay, so let's differentiate. F prime of x equals, okay, derivative of x cubed is 3x squared minus 6x, and the derivative of 36, which is a constant, is 0. Then from here, what shall we do next? Rather, we equate the first derivative to 0. Okay, f prime of x equals 0 to solve for the critical numbers. Okay, 3x squared minus 6x equals 0. Okay, so how shall we solve for x here? Okay, how shall we solve for x? Okay, this is quadratic. Yes, this is a quadratic equation, and it could be factored. Take note that this is factorable, and there is a common monomial factor, which is 3x. Okay, so let's factor it out as 3x times, okay, x minus 2 equals 0. Now, by zero product property, we equate each factor to 0 to solve for x. Okay, 3x equals 0, and then x minus 2 is equal to 0. And from here, we can now find x values. X is equal to 0 and x is equal to 2. So, for problem number 2, how many critical values are there? Critical numbers, I should say. Critical value is different. Critical numbers. Okay, so we have identified 2 critical numbers for number 2. These are 0 and 2. Okay, so you'll find the significance of critical numbers in the next slides. Now, we proceed to the next. Let's see absolute extrema. What do we mean by absolute extrema? Absolute minimum and absolute maximum. Let's see be an element of the domain of the function. So let's see be an element of the domain of the function. If, okay, number 1, f of c is an absolute maximum, let me underline, it is an absolute maximum if f of c is greater than f of x for all x in the domain. Maximum. Okay? And when is it an absolute minimum? If f of c is less than f of x for all x in the domain of the function. Now, as long as the function is continuous or continuous, there is an absolute maximum and minimum. How do we identify? The next question is, how do we identify the absolute maximum and minimum? We have step number 1, identifying the absolute extrema. We follow these steps. Number 1, find the critical numbers. Okay? Find the critical numbers, and that's just what we did. And then number 2, find the critical values. Critical value. So, there is a difference between a critical number and a critical value. Critical number is the x value. Now, once you evaluated the function at that particular x value, that will give the critical value. So, there is a difference between critical number and critical value. Okay? Critical number is just the x value. Critical value is the function value at that particular x value. Next, find the value at the endpoints. Endpoints, remember that we said a while ago that the function is defined in the closed interval AB. Okay, A, B. You know that this is an interval. It's a closed interval. So you have to find also the function value at the endpoints f of A and f of B. Next, the greatest function value in step 3 will give the absolute maximum, while the smallest function value in step 3 will give the absolute minimum. Okay, for instance, find the relative extrema of the function f of x is equal to x squared plus 3x, okay, in that interval -2, 1. Okay, -2, 1. Once again, the function given is x squared plus 3x, and the interval is -2, 1. Okay, so go back to the steps. Number 1, find first the critical numbers, then the critical value, then the value of the function at the endpoints A and B, and then identify which one is relative or absolute max, okay, and which one is the absolute minimum. The greatest function value is the absolute max, while the smallest function value will be the absolute minimum. Okay, so let's look into problem number 3. So step number 1, identify the critical values. Critical numbers. Okay, I'm always using critical values. No. Identify or find the critical numbers. Again, how do we obtain the critical numbers? We take the first derivative and equate it to 0, solve for x. Okay, so f prime of x equals 2x plus 3. 2x plus 3. Then from here, we can now identify our critical number. There is only one, because this one is quadratic. Okay? A quadratic function, remember, has either a minimum or a maximum. Because if you recall, the graph of a quadratic function is either a parabola that opens upward or a parabola that opens downward. So it has an either a relative or an absolute maximum or minimum rather, or a maximum. Okay? The given is quadratic. Okay, x squared plus 3x. So expect that there is only one critical number. Okay? So in this case, the critical number is 2x equal to -3, x is equal to -3 halves. Okay? -3 halves or -1.5. Now, Step number 2 says, we find the critical value. Take note that this is the critical number. Okay? Now, what about critical value? The critical value is the function value at x equal to negative 3/2 or at the critical number. We continue here. Okay, the function is our f of x equals x squared plus 3x. F prime of x is 2x plus 3. 2x plus 3 equals 0. X is equal to negative 3/2. That's our critical number. Now, to find the critical value, we evaluate the function at negative 3/2. Okay, the function value at the critical number. So, f of negative 3/2 is negative 3/2 squared plus 3 times negative 3/2. Okay, and what is it equal to? Okay, 3/2 squared is 9 over 4. Okay, minus 9 over 2. And what is 9 over 4 minus 9 over 2? This is negative 9 over 4. Okay, it's negative 9 over 4. So, we're done with step A. Let me label. Step A is identifying the critical number. Step B is finding the critical value. And C, okay, letter C. We proceed to letter C. What is step number 3? Find the function value at the endpoints. Remember, the interval provided or the given interval is negative 2, 1. Okay, negative 2, 1. So, let's take f of, so this is now letter C, f of negative 2. Okay, so let's have f of negative 2. Where did I get f of negative, where did I get negative 2? From here. Okay, the endpoints of our interval. Okay, negative 2. F of negative 2 is, okay, negative 2 squared plus 3 times negative 2. Okay, what is this equal to? Okay, 4 minus 6, which is negative 2. Okay, negative 2. Next, how about letter C, letter D? How about letter D? Oh no, we're not done yet with letter C, or step number 3 rather. We also have to evaluate the function at the other endpoint, f of 1. What is f of 1? Okay, so if this is f of 2, then f of 1 is, okay, f of 1, the other endpoint is 1 squared plus 3 times 1. And this is equal to 1 plus 4, which is equal to 1 plus 3 rather. 1 plus 3 or 4. The final answer should be 4. 1 plus 3, which is equal to 4. So, this must be, okay, going back. Let me erase this first, so that we can identify now our absolute max and absolute mean. Go back to number 4. What does it say? The greatest function value, look, the greatest function value in step 3 will be the absolute max, while the smallest function value will be the absolute mean. Okay, the absolute minimum. Okay, within that interval. So, comparing now, negative 9 over 4. Look at this. Negative 9 over 4, negative 2, and 4. Which one is the greatest? The greatest is 4. Therefore, this is the absolute max. This is the absolute max. And what about the absolute mean? The smallest value, the least value is this. Negative 9 over 4. Okay, this is the absolute minimum. Okay, this is the absolute mean, while 4 here is our absolute max. How many function values did we compare? 3. This is one function value, another function value, and another function value. Okay? So the greatest gives the absolute max, and the least or the smallest value gives the absolute mean. So negative 9 over 4 is less than negative 2. And the greatest of them all is 4. Then that makes 4 to be the absolute max. Next. Now, what about, okay, f of x is equal to x cubed minus 15x minus 5 given the closed interval negative 3 and 1. Find the relative. I'm sorry, did I use absolute? That is supposed to be relative. Okay? Relative yan. Please make the necessary corrections. This is not absolute but relative. Okay, this is supposed to be relative because it depends upon the interval given. Because in this interval, we mean within this interval, from negative 2 to 1, the relative minimum, sorry, please make the necessary correction. This is relative. That means with respect to the given interval. Okay, with respect to this given interval, the relative minimum is negative 9 over 4 and the relative maximum, relative, because this may change. Okay, so it's not an absolute mean, it's not an absolute max, it's relative minimum and relative maximum. So, depending upon, it may vary depending upon the interval given. But for this particular problem, the interval is the closed interval from negative 2 to 1 inclusive kasi closed siya. Now, we proceed to problem number 4. How about a cubic function? F of x is equal to x cubed minus 15x minus 5. And the closed interval, within the closed interval, negative 3, negative 1. Okay? Negative 3, negative 1. Okay, so let's follow the steps, 4 steps once again. Let's copy first the function given, f of x. The function is f of x equals x to the 4th minus 8x squared plus 16. Is this the given? Or x cubed minus, I'm referring to the next. Ba't nawala? Okay, let me add one more. New notebook. Okay. F of x equals x cubed minus 15x minus 5 closed interval negative 3, negative 1. Okay, so find the relative extrema. Find the relative by relative extrema, we mean either relative max or relative. Okay? Relative max or relative mean. Okay? Relative minimum. Okay, just the same, we proceed to step letter A. Take the first derivative, equate it to 0 to find the critical number. So, f prime of x equals 3x squared minus 15. Okay? 3x squared minus 15. Equating this to 0 to get the critical number. Okay, 3x squared minus 15 equals 0. Okay? 3x squared equals 15. X squared is equal to 5. So, x is positive, negative, square root of 5. Anything more? Wala, because this is cubic. Okay? Cubic function. So, two critical values or two critical numbers rather. Critical numbers. Now, we proceed to step B. Evaluate the function at the critical values or critical numbers rather. We find f of square root of 5 and f of negative square root of 5. Okay, what is f of the square root of 5? That means square root of 5 raised to the third power minus 15 times the square root of 5 minus 5. Okay, what will this be? This one will be 5 square root of 5 minus, okay, 5 square root of 5 minus 15 square root of 5 minus 5, which is negative 10 square root of 5 minus 5. Okay, how about f of negative square root of 5? Okay, negative square root of 5 to the third power minus 15 times negative square root of 5 minus 5. So let's simplify further. This will be negative, okay, negative 5 square root of 5 plus 15 square root of 5 minus 5, which when simplified is 10 square root of 5 minus 5. Okay? Get your calculators and express it to the nearest two decimal places so that we can identify which is the greatest and which is the smallest. But we're not done yet. We evaluate also, okay, critical values. These two are the critical values. Okay, these are critical numbers and these are critical values. We're not done yet. We also have to evaluate the function at the endpoints. Okay, at the endpoint. So, may I copy? So, find f of, we also have to look for f of negative 3 and f of negative 1. And we will, okay, identify which among the function values is the greatest and which one is the least or the smallest. So, f of negative 3 is negative 3 cubed minus 15 times negative 3 minus 5. What will this be? Negative 3 cubed is negative 27 plus 45 minus 5. Okay, this is negative 27 plus 45 minus 5 is 13. Okay, how about f of negative 1? That will be negative 1 cubed minus 15 times negative 1 minus 5 is negative 1 plus 15 minus 5 is 9. Which among the two critical numbers rather is contained in the interval negative 3, negative 1? Which among our two critical numbers, okay, belong to that interval negative 3, negative 1? It's only negative square root of 5. Okay, only negative square root of 5 because square root of 5 is no longer contained here. So, disregard this portion. This one is the relative mean and this is the relative max. Okay. However, if we change this into, if I change the interval into, let's say, from negative 3 to 3, okay, if we change the interval given in, to negative 3 to positive 3, then we could include square root of 5. Okay, I hope that is clear now. Did you get the point of Jade? Did you get this point? Okay. So this is why we cannot include this. Cross it out. Cross it out. We cross this out because it's not contained in the closed interval provided. The closed interval, which we overlooked, is negative 3, negative 1. If I change it into, let's say, negative 3, 3, negative 3, 3, then this will be included, square root of 5. Okay? Shall we proceed to the next? Can we move on to the next? Okay, let's proceed to the next example then. Once more, going back, we said a function is increasing if f prime of x is greater than 0. And it is decreasing if f prime of x is less than 0. Now, let's look into the illustration. Any other question before we proceed? Okay, once more, f prime of x, its geometric meaning or implication is the slope of the tangent line. So, looking at this, from A to C, okay, A to C, the function is increasing, isn't it? From here, from A to C, the function is increasing. Now, what can you say from C to B this time? From C to B, okay, from C to B, the function is decreasing. So, let me write that f prime of x is less than 0 in BC. Okay? Once more, from A to C, the function is increasing. But from C to B, the function is decreasing. F prime of x is greater than 0 from A to C. F prime of x is less than 0 in CB. CB baligtad. Okay, C from C, CB. Okay, erase this. Okay, CB. Next, what did we say about that? If f prime of x is greater than 0 for all x in AC and f prime of x is less than 0 for all x in CB, then f prime of x is a relative maximum. Okay? Then, f prime of x, okay? If this is satisfied, then f prime of x is a relative maximum. Okay, it's a maximum. Going back, if f prime of x is greater than 0 or positive for all x in AC, and f prime of x is less than 0 for all x in CB, then f prime of x is a relative maximum. What about a relative minimum? For a relative minimum, it's the other way. Okay? We start from decreasing, increasing, relative mean. If f prime of x is less than 0 for all x in AC, and f prime of x is greater than 0 for all x in CB, then f prime of x is a minimum, relative minimum. Let's look into this part of the graph. Or let me draw another curve. Say A, B, and C is here. Okay, C. The condition says, or the first derivative test says, if f prime of x is less than 0, meaning negative. Okay, negative. In AC, and f prime of x is greater than 0 in CB, then f prime of x is a relative minimum. Okay? It's a relative mean. Look at this graph. This is our interval AC. From A to C, what can you say about the graph? It's decreasing, yes? It's f prime of x is less than 0 or negative. F prime of x is negative or less than 0. But from C to B, okay, C to B, within this interval, C to B, what happens? F, the function is increasing. The function is increasing. So, f prime of x is greater than 0 in CB. Therefore, f prime of x is a relative minimum. Okay? F prime of x is a relative minimum. Number 3, if f prime of x is greater than 0 or f prime of x is less than 0 for all x throughout the interval AC, then f prime of x is neither a relative nor, okay, relative max nor a relative min. Okay, what is it? We will find out later. Now, let's look into example number 6 and illustrate what we mean by the first derivative test. Okay, just the same, find the relative extrema, this time using the first derivative test. Once again, the first derivative test says, if the first derivative is positive from A to C and negative from C to B, then it's a relative max. Or to the left of C, but we enclose or within that interval AB, or you choose any x value here, okay, any x value, and if its derivative f prime of x rather is positive, okay, positive, look, here positive and negative, that means Positive, negative means relative max. Okay? From positive to negative, relative max. However, if it is from negative, pababa, to positive, it's a relative mean. Relative minimum. From negative to positive, it's a relative minimum. Let's illustrate by using or by answering problem number 6. Find the relative extrema of the problem, or should I say the function f of x equal to 2x cubed. We're now moving on to problem number 6. Find the relative extrema or relative extreme of f of x equal to 2x cubed plus 3x squared minus 12x. Okay, so first thing we have to do is to identify the critical numbers. So how different is this from the previous? We did not identify anymore. I did not specify anymore an interval. Okay, but rather we will identify, the extreme values, or should I say the critical numbers, I should say. So critical, finding the critical numbers, take the first derivative, f prime of x equals 6x squared plus 6x minus 12. And then we set this to 0 to find the critical numbers. 6x squared plus 6x minus 12 equals 0. Okay? Now, we could factor this out. This is factorable. 6 is common to all the 3 terms. So, we could bring it out, giving x squared plus x minus 2 equals 0. Okay? And this one is factorable. And we divide both sides by 6 to eliminate 6, leaving x squared plus x minus 2 equals 0. So this is quadratic and it's factorable. Okay? What are the two factors of this quadratic function? We have x plus 2 and x minus 1. X plus 2 and x minus 1. Equating each factor to 0, x plus 2 equals 0, x minus 1 equal to 0. So we have now two critical numbers, 1 and negative 2. So our critical numbers are negative 2 and 1. Now, what are we going to do next? Find the critical points. Okay, letter B. Find the critical points. Okay, a point is denoted by a pair of numbers x, y. So what do we have? X values. So to find the critical points, then we evaluate the function at the critical numbers. We are to find f of negative 2 and f of 1. Okay? What is f of negative 2? That's 2 times negative 2 to the third power plus 3 times negative 2 squared minus 12 times negative 2. And let's simplify. What will this be? This is 8. Negative 8 times 2, negative 16. Negative 16, and this will be plus 12 plus 24. Okay? And what is it equal to? Negative 16 plus 12, that's negative 4. Negative 4 plus 24 is positive 20. Okay? So this is equal to 20. So one critical point that we have identified now is negative 220. What about the other critical point? Evaluate the function at the critical number 1. So, f of 1 equals 2 times 1 cubed plus 3 times 1 squared minus 12 times 1. And what is it equal to? This is 2 plus 5. That's 5 minus 7 or minus 12 is negative 7. Correct? Okay. So 2 plus 3, 5. 5 minus 12 is negative 7. So the other critical point is 1, negative 7. Once again, how did we identify the critical points? The critical points are obtained by first evaluating the function at the critical number. Our critical numbers are negative 2 and 1. So f of negative 2 is positive 20, so negative 220. F of 1 is negative 7, so we have 1, negative 7. These are our critical points. Now we are ready to test for relative extrema. Okay? Relative extrema. What are our critical numbers? Negative 2 and 1. We will test a value to the left of negative 2 and to its right. In like manner, we will also identify a value or a number, an x value, to the left of 1 and to its right. And remember, what did we say? From positive to negative, it's a max. Okay? From negative to positive, it's a min. First derivative test. Okay, let me unclose this. If f prime of x is changes from positive to negative, it's a max. If f prime of x changes from negative to positive, it's a min. Okay? So, let's continue to step number 3. Letter C now. Test for relative extrema. Okay, let's have x equal to negative 2. Our first critical number. Okay, I want you to identify, so let's prepare a table which looks like this. Okay, your f prime of x, and identify a value which is x is less than negative 2, meaning to the left of negative 2, and a value which is to the right of negative 2. And do the same for x equal to, what's our other critical number? Positive 1. Find the sign of f prime of x for x less than 1 and for x greater than 1. Okay? So for x less than 1 and greater than 1. Okay, identify an x value which is less than negative 2. Okay, identify an x value less than negative 2. Maybe we could identify or make use of negative 3. To its left, okay, to its left. Okay, now find f prime of negative 3. F prime of negative 3. Okay, what is it equal to? F prime of negative 3. What is our f prime of x a while ago? This one. Let's copy first. Okay, let's put it here. Okay, let's have it here. Okay, so what is f prime of negative 3? That will be 6 times negative 3 squared plus 6 times negative 3 minus 12. Okay, what will this be? 3 squared, 9. Okay, 9 times 6 is 54. 54 minus 18 minus 12 is positive 24. This minus 18 minus 12, it's positive 24. So, I shall write here positive. Okay? F prime of x, okay, f prime of x is positive for a value which is located to the left of negative 2. How about to its right? Okay? How about to the right of negative 2? Move muna natin to. Okay, let's go back. What about a number which is found to the right of negative 2? Let's say negative 1. Okay? Or if you want 0, it's okay. 0 anyway is to the right of negative 2. So let x be, let x be 0, okay, or negative 1 if you like negative 1. So, f prime of negative 1 equals 6 times negative 1 squared plus 6 times negative 1 minus 12. From here, okay, simply evaluate this at negative 1. So, 6 x raised to, okay, 2 or negative 1 squared plus 6x times negative 1 minus 12. And let's simplify further. F prime of negative 1 is equal to 6 minus 12, which is negative 12. So, negative. Okay? So, from negative, positive to negative, what can you say then? That f of negative 2, this gives this x value, which means that this x value, this critical number, gives a relative maximum. Okay? That this x value, let me write, this critical number now it's not very visible, so let me use another color. This critical number gives a relative max. Okay, it gives a relative max. What then is the relative max? Next question is, what is the relative max? What then is the relative maximum? The relative maximum is the function value at x equal to negative 2. Okay, the function value at x equal to negative 2. What is the original function given? Okay, the function given is 2x cubed plus 3x squared minus 12x. So, to get then the relative max, you evaluate the function at x equal to negative 2. So, 2 times negative 2 to the third power plus 3 times negative 2 squared minus 12 times negative 2. Okay, why? The original function is this. Okay, this is the original function. So to get the relative max, we evaluate the function at x equal to 2 or negative 2, I should say. So f of negative 2, let's continue. F of negative 2 equals, okay, negative 2 cubed, that's 8, 16, okay, plus 12, okay, plus 24. Okay? Negative 12 times negative 2 is 24. And this one will give, okay, 36 minus 16 is, answer is 20. What is 20 then? This is our relative max. Okay? So this is our relative maximum. Next, testing for x equal to 1. So our other critical number is x equal to 1, just like what we did in the previous. Identify a value to its left and a value to its right. Again, what did we say? From, okay, take note of the first derivative test. If f prime of x changes from positive to negative, it's a max. From negative to positive, bakit may negative 1 ako? Okay, it's a max. And then from negative to positive, it's a min. Okay, so x less than 1, we could have x equal to 0. And x greater than 1, we can have x equal to 2. How shall we test? Use the first derivative. That's why we call it first derivative test. Okay, using the first derivative for testing or identifying the relative max and min. So for x equal to 0 and x equal to 2, f prime of x, once again, is f prime of x is equal to, from the previous, is 6x squared plus 6x minus 12. Okay, so what is f prime of 0? F prime of 0 is 6 times 0 squared plus 6 times 0 minus 12. F prime of 0 is negative 12. So, from negative. Positive kaya if it's x equal to 2. Let's see. F prime. Take note, it's f prime because we're using the first derivative. F prime of 2 equals 6 times 2 squared plus 6 times 2 minus 12. Okay, so f prime of 2 equals 24, okay, plus 12 minus 12 is 24. So f prime of 2 is 24, which is positive. So what can you say? What can you say then? Okay, what did we say? From negative, that's decreasing, pababa. Tapos biglang aakyat. So, minimum siya. You get that? Okay. So, from negative to positive, f prime of x greater than or less than 0, and becomes here f prime of x greater than 0, then it's a minimum. Okay? So, minimum. Which means that this function value or this x value gives a minimum. The next question is, what is the minimum? That's the value of the function at 1. We did that already and we found out that it's equal to negative 7. It's here. Saan na yun? Ayun, no? Okay? Yan, no? F of 1 is negative 7. F of 2 is 20. This is a relative max and this one is a minimum. Okay? Minimum. We stopped at this part. So just to show you once again, what is the relative mean? It's simply evaluating the function at 1. Okay, so the original function is 2x cubed, so 2 times 1 cubed plus 3 times 1 squared minus 12 times 1. And when simplified, this is equal to negative 7, which means that this must be our mean. Okay? This is our Now, if I would ask you, how would the graph look like? Having identified that, okay, having identified this, how would the graph look like? So, we roughly sketch the graph, or prior to graph sketching, may we skip that portion? We will have that in the next, when we shall have taken up the second derivative test. Okay, it would be easier to graph now because we know at which point will the graph has its highest point and its lowest point. Before we proceed to that, may we continue with the second derivative test. Now, if there is a first derivative test, we also have a second derivative test. The second derivative test says if f is continuous on the interval AB, meaning no gap, and f prime of x exists, and f double prime of x exists, if f double prime, this time second derivative, if f double prime is positive or greater than 0, then f of c is a relative minimum. Okay? So, baligtad. If f double prime is greater than 0, it's a mean. If f double prime is positive, it's a, okay? Once more, if f double prime is positive, it's a mean. If f double prime is negative, it's a max. If f double prime is 0, what is it? We'll find out later. Okay. How do we sketch polynomials using the second derivative test? Or even using the first derivative test? Step number 1, we have to find the x-intercepts. Step number 2, find the relative extrema by first identifying the critical numbers, then critical points, test for relative extrema using either first derivative or second derivative test, test for few points in the interval, and then connect the points. Okay, let's show using one example. Okay, the second derivative test says if f double prime of c, the critical number, if f double prime of c is positive, it's a relative mean. If f double prime of c is negative, it's a relative max. That's the second derivative test. Okay, so sketch the polynomial function x to the fourth minus 4x squared, okay, plus 4. How shall we do that? We follow the steps as listed here. Find the x-intercept. Now, why did I postpone graphing this? Because I did not yet discuss with you step number 1. Finding the x-intercept so that we would know in which, okay, at which points the graph will intersect the x-axis. Okay, that's the x-intercept. Saan ba siya mag-pass by sa x-axis? That's finding the x-intercept. That's step number 1. And then the next 3 other steps. So let's show this by using this example. F of x is equal to x to the fourth minus 4x squared plus 4x. Okay, so like what we did in the previous, step number 1 is identifying the critical numbers. Let me copy the function given. F of x is equal to x to the fourth minus 4x squared plus 4. Okay, so step A, instead of, okay, instead of the critical numbers, we have additional step here. Find the x-intercepts. Okay? X-intercepts muna. Find the x-intercepts. Okay, how do we find the x-intercepts? Take note that your x-intercepts are the values found along your x-axis, which means y is 0. Okay? So to find the x-intercepts, equate the function to 0 and solve for x. Okay? Equate the function to 0 and solve for x. Okay, let's do that here. X to the 4th minus 4x squared plus 4 equals 0. Okay? Now, the quadratic expression on the left side is factorable. We can factor this out as a perfect square, right? X squared minus 2 and x squared plus 2. Oh, sorry, minus 2. It's a perfect square. Sorry. Ano aking eraser? Okay, x squared minus 2, x squared minus 2. Or, in a concise manner, x squared minus 2 raised to the second power. Okay, that's it. Then from here, extracting the square root, x squared minus 2 equals 0. Okay, so x equals positive and negative square root of 2. Okay, so we have positive, negative, square root of 2. These are our x-intercepts. Take note, these are not critical numbers yet. X-intercepts, which means that the function or the graph, the function passes through okay, square root of 2, 0, and negative square root of 2, 0. Okay, along the x-axis. Intercepts. Letter B. Find the critical numbers. Okay, critical numbers. How do we get the critical numbers once again? We take the first derivative. Okay, get the first derivative f prime of x and then set it to 0. It's 4x cubed minus 8x. And then equating this to 0 equals 0. Then we can factor this out. X squared minus 2 equals 0. Okay? So, what will be our critical numbers? X equal to 0 and x equal to positive, negative square root of 2. So, how many critical numbers do we have? Our critical numbers are 0, negative square root of 2, and square root of 2. Okay? Next, our critical points. Numbers pa lang yan. So, critical points, that's next step. Critical points. The critical points are, okay, for x equal to 0, find f of 0. What is f of 0? Again, the function given is, okay, let me copy the function. Ayan. Okay, so f of 0 is 0 to the 4th. 0 to the 4th minus 4 times 0 squared plus 4, it's equal to 4. So, one critical point is 0, 4. Okay, xy. One critical point is 0, 4. What are the other critical points? Okay, the other critical points are at x equal to square root of 2 and at x equal to negative square root of 2. But we said a while ago that these are the intercepts, x-intercepts. So they are contained in the point, okay, wait. These are contained in the point square root of 2, 0 and negative square root of 2, 0. Because when we speak of x-intercepts, we mean this, eto. These points contain the x-intercepts. Okay, this, and this. These are the points containing the x-intercept. So if this is A, this is point, let's say, A, and let this be B and C. Okay, this is A0, correct? This one is B0, and this is C0, correct? C0. So if, going back, if positive, negative 2 are intercepts, then they are contained in the point square root of 2, 0 and negative square root of 2, 0. You don't have to solve for the function value at negative square root of 2 and positive square root of 2 because you'll end up with 0. Okay? So we have identified already our critical points. How many critical points do we have? Tatlo. Okay, 0, 4, square root of 2, 0, and negative square root of 2, 0. Next, we will use now, instead of the first derivative, I will use the second derivative. Okay? So, testing now for test C. Test for min and max. Using the first derivative or the second derivative test. Once more, the second derivative test says this. If, okay, let me put on this side, if f double prime of C is greater than 0 or positive, it's a min. If f double prime of C is less than 0, it's a max. Okay, it's a max. So, f double prime of 0. What are we going to test? Our critical numbers. Our critical numbers are x equal to 0, square root of 2, and negative square root of 2. Okay, so f double prime of 0, what is it equal to? Take the second derivative muna. Okay, so f prime prime of x is, what is f prime prime of x? Okay, from the previous, we have already f prime. Okay, so this is f prime. 4x cubed minus 8x. Get the f double prime. It's 12x minus 8. Okay, so f double prime is 12x minus 8. Once more, where did we get this? From here. Get the second derivative, 12x minus 8. So, f prime prime of x. But what x's are we going to check? Our critical numbers. So, find f double prime of 0. What is f double prime of 0? Okay, 12 times 0 minus 8 is, okay, negative 8. And since this is less than 0, what can you say? At x equal to 0, the function FCN has a max. Okay, relative max. from here, from this test, the second derivative test. Next, so we're done with this. We proceed to f. Okay, x equal to square root of 2. What is f prime prime of square root of 2? Okay, what is it equal to? F prime prime will be 12 times the square root of 2 minus 8. And what is this equal to? Okay, for f prime prime of f double prime of the square root of 2 is, okay, get your calcu and you can verify, okay. Square root of 2 times 12, square root of 2 is 16, diba? 16.97. Okay, let's check on our f prime prime. From here, this is supposed to be squared. Yes, this is supposed to be squared. Minus 8. So if you square this, but it will yield the same anyway. From here, okay? If we continue getting the second derivative, then f prime prime will be 12x squared minus 8. Okay, correct. 12x squared minus 8. Okay, so f prime prime is (12x squared minus 8). So this one will be, when evaluated, gives the radical sign will be eliminated. That's 24 minus 8 is 16, correct? So this one will be 16. And 16 is, what can you say about 16? It's greater than 0. Therefore, at x equal to square root of 2, the function has a min. Okay? From here. Minimum. Next, how about f double prime? What about f double prime of negative square root of 2? F double prime of negative square root of 2, 12 times negative square root of 2 squared minus 18 equal to, just the same, this will be 16. And 16 is greater than 0. So, at x equal to negative square root of 2, the function FCN has a min. So now we have identified our, okay, relative, max, and min. Then we are ready to draw the graph or sketch the graph. Let me write. What are the critical points that we have identified so far? Critical points. Okay, the critical points are 0, 4, 0, 4, square root of 2, 0, negative square root of 2, 0. Negative 2, negative square root of 2, 0. Which among these three gives the maximum point? This one is the relative max. Okay? This is the relative max. Saan galing yan? From here. Ito, oh. We said here that at x equal to 0, the function has a maximum. But when x is 0, what is the function value? When x is 0, what is the function value? It's here. Okay, when x is 0, saan yung computation natin? When x, f of 0, where is f of 0? Oh, there. Okay? f of 0 is equal to 4, which means that 4 is the relative max. Okay, our critical points are 0, 4, okay, square root of 2, 0, negative square root of 2, 0. Now let's proceed. Critical points are 0, 4, square root of 2, 0, negative square root of 2, 0. Why did we say that this is the relative max? But that's from the second derivative test. How about this? What can you say about the second point? Okay, what can you say about the second point? F double prime of square root of 2, what did we get? F double prime of square root of 2 is 16, which is greater than 0. And the second derivative test says it's a min. Okay, so it's a minimum. This is a relative min. And lastly, this also is a relative min. So how shall we graph the function now? So draw your axes x and y. Okay, your critical numbers are 0. Okay, 0, square root of 2, square root of 2 is 1.4 something. So let this be 1, let this be 2, let this be negative 1, let this be negative 2. Okay, 2, 4. Okay, let this be 1, 2, although not equally spaced. 0, 4. Okay, locate this point. 0, 4 is this. Our intercepts are, okay, this point, square root of 2, 0. Square root of 2, 0 is somewhere here. Okay, so let me use bakit binura ko? So somewhere here, square root of 2, 0, and negative square root of 2, 0. So, okay. Now, what did we say about negative square root of 2, 0? It's a min. It's a min. It's a minimum. Meaning, it will, if this is the minimum, this must be the lowest point. So, expect that the graph, okay, the graph would climb up here, and this will move up to until it reaches that point, 0, 4. Once again, it would look like this. Okay, so the graph would look like that. So roughly sketching the graph now, the graph would look like this. You may add other points. You may want to evaluate the function at x equal to negative 2. So to be sure, you can add x equal to negative 2. What is f of negative 2? Okay, the original function, our original function is f of x is equal to x to the fourth, okay, x to the fourth minus 4x squared plus 4. So f of negative 2 will be negative 2 to the fourth power minus 4 times negative 2 squared plus 4. Okay, negative 2 to the fourth is 16. Okay, minus 16. Okay, plus 4. That will be negative 2, 4. So, correct. Negative 2, 4 is somewhere here. Correct ako? Okay, negative 2, 4 somewhere here. Kaya, we are very sure that the graph would climb up. Okay? And here also, after 1.41, you can select 2. If x is equal to 2, then f of 2 will be, okay, 2 to the fourth minus 4 times 2 squared plus 4. Okay, and this one will give 16 minus 16, 4 din siya. So, dito rin siya. Okay? So, for sure, the graph would climb up in this manner. Okay, so that's the graph. So, we have sketched the graph. We were able to sketch the graph. So, the graph would look like that. Other questions? Once more, let's go over the steps. Number 1. Okay, number 1, identify the, where did we? Yan, intercepts. Identify the intercepts and then the critical numbers by finding the first derivative. For intercepts, equate the function to 0, solve for x. For critical numbers, okay, find the first derivative, equate it to 0, solve for x. Critical points, evaluate the function at the critical numbers identified, okay? And then use second derivative test to tell whether, okay, the function value given by a critical point is max or min. When is it min? If f double prime is positive. Okay? When f double prime of c is negative, then it's a max. Okay? So, connect. First, locate the points and connect using a line. And that's it. Last for this morning, this is an application of the absolute extrema, extremum, minimum optimization problems. Okay, for word problems, application of extreme values, there are steps. The first step is draw and label all the variables. Determine the quantity to be maximized or minimized. Then set up an equation, quantity for that quantity. Express it in terms of one variable only. If possible, we use the given information and relationship between quantities to eliminate some other variables. And then number 4, find the minimum value, maximum value by solving first for the critical points and then determine which one will give maximum, minimum using either first derivative test or second derivative test. Let's look at one example. A rectangular box is to be made from a piece of cardboard 24 centimeter long and 9 cm wide by cutting out identical squares from the 4 corners and turning up the sides. Find the volume, okay, of the largest rectangular box that can be formed. Okay? So from the problem, we could easily identify which quantity is to be maximized or minimized. Find the volume of the largest rectangular box. Largest rectangular box that can be formed out of this. So you have a cardboard, which is 24 centimeters long and 9 cm wide. And then after that, you cut out 4 squares. Okay, 4 squares because from each corner. So if you cut out, this will no longer be 9 cm and the length will not be 24 cm anymore because we will cut this out. Now, suppose this, okay, is S. So, if I cut out S here and S here, then that means 24 minus S, or 24 minus 2S. That will be the new length. And then, on the width, I will cut out S here and S here. That means the new width will be from here to here. That's 9 minus 2S. Okay? 9 minus 2S. Let's have it here. Now, time is running out. I will continue. You can watch it later. Okay, you may exit. Okay lang. Are there questions at this point? Cleanse and Jeric, yes. Yung second derivative should be 12x squared. Yes, yes. Okay, correct. 12x squared minus 8, the previous example. Okay. Okay, you may exit, but I will continue with the last part and you can view it later. Okay, because I know you still have a class in the afternoon. Let me just finish all of the slides I have prepared this morning. So for problem number 1, optimization, like what we have just enumerated, the steps are, if you could draw a diagram or a figure representative of the problem, do so. Then after that, identify all the given, all the knowns and the unknowns. And for the unknown variable, we use a or should I say, for the unknown, we make use of a variable. You may use S, X, or any letter for that matter, okay? So for this problem, going back, rectangular box, you know how a box looks like. Okay, a rectangular box is to be formed by cutting, okay, a cardboard 24 cm long. So originally this is 24 cm and its length is 24 cm and its width is 9 cm. But we are to cut out squares from each corner. Okay, cutting out squares from each corner, and let's say, let S be the size, okay, the size of, or should I say, the length of the side of the squares. Okay, so we let S, yan, we made use of S to represent the side of the square that is to be cut out. S ito, S, S, S. Okay, you know that a square has equal sides. So if I will cut out S from both sides, from both ends, then what happens to 24? 24 here becomes 24, the new, okay, or the length of the box, the rectangular box that will be formed will simply be 24 minus 2s. Okay, what is this 24 minus 2s? It's this segment here. Okay, in like manner, if we cut out s and s from the width, then this one must be 9 minus 2s. Take note that I did not include the unit yet. Okay, going back to the problem, what is it asking for? Volume. Okay, find the rectangular, find the problem says, find the volume find the volume of the largest rectangular box that can be formed out of this. So, we know that volume of a rectangular box volume is simply equal to area of the base times height. Yes, area of the base times height. Times height. Okay, so volume of this box, the rectangular box that we are to construct, is equal to, now imagine that we will fold this, okay, along the dotted line now. So we are now to form, okay, the rectangular box. Forming the rectangular box, we will now end up with, okay, the area of the base, which is 24. The base has a length of 24 minus 2s. So I'm going to write 24 minus 2s. That's the length times width. The width of the base is 9 minus 2s. And its height is s. Okay, so v equals multiply. What will this be? This will be equal to 24 minus is, when simplified, this will give us 2 times 108s minus 33s squared plus 2s cubed. Because you'll have s times s times s will be s to the third power. The space is not enough, so maybe have it here. The volume will be V expressed in terms of S is equal to area of the base. The base is a rectangle, okay? Length times width. Length times width times the height, okay? So the volume in terms of S is equal to the length, which is 24 minus 2S. The width is 9 minus 2S. And the height is S. Okay? Get the product. Okay, what will this be? 24 times 9 times S is 216S. Okay? Minus 24 times 2S is negative 48. A negative 48 s squared, okay, minus 18 s squared plus, okay, 4s cubed. Correct? That's after multiplying 24 by 9, 216 times s is 216s. 24 times negative 2s times s is negative 48s squared. Negative 2s times 9 times s is negative 18s squared. And finally, negative 2s times negative 2s times s is plus 4s cubed. Now we are ready to take its derivative. So since the volume is the quantity to be maximize largest volume. Your clue there is the problem stated largest volume. So this is the quantity that we are to differentiate. Okay, we have to get its derivative. So V prime of S, okay, V prime of S is equal to, get the derivative, 216 minus, okay, get the sum of the two, get the sum of this will be 48 plus 18 is 66, okay, times, yan, 66 times 2, 132, correct? 132 s plus 12s squared. 12s squared. Then from here, this is the quantity to be maximized. Then, this is the equation or formula. Then after that, A, B, and C differentiate. D, find the critical number. Okay, so from here, 216, 216 minus 132s plus 12s squared equals 0. Okay, take note that this can be reduced to 4 times 54 minus 33s plus 3s squared equal to 0. And divide it by 4, we'll end up with 54, or we can rewrite this into 3s squared minus 33s plus 54 equals 0. And factor it out as 3s minus 6 times s minus 9 equals 0. Okay? So this is factorable by factoring. Okay, factoring, and then solve for s. 3s minus 6 equal to 0, and s minus 9, s minus 9 equals 0. 3s is equal to 6, s is equal to 2. And what about here? S equal to 9. Okay, s is equal to 9. However, take note that the dimensions of the rectangle, our rectangle is only, the cardboard is only 24 by 9, which means this is, okay, outside already. It's outside the interval. Remember the point raised by Jade? Okay, it's outside the interval. So it's impossible. It's impossible to cut out all of them. Then if we cut it out, then we cannot form anymore a rectangle. So we cross this out. Why? Because it's outside. It's outside the interval. Remember that our cardboard is only 24 cm long and 9 cm wide. Okay, so we shall consider s equal to 2. Okay, so since this is the critical number, now we can find the volume. So volume in s, in terms of s, is now equal to 24, okay, minus 2s. Remember the formula that we have put up a while ago, 9 minus 2s times s. So 24 minus 2 times 2, okay, times 9 minus 2 times 2, okay, times 2. Now let's simplify further. That's 20 times 9 minus, that's 5, and then times 2. And the answer is 200. Okay, we answered the problem. 200 cubic centimeters. So if we cut out a square in which the side is, so what will be the dimensions of the box? So if this is the box, then it is by, so we cut out, ito is 7, sorry, it's not 7, it's 5 rather, no, sorry, it's 24 minus 2s, so 24, it's 20 rather. Then the dimension, if the problem calls for dimensions of the box, then it will be the rectangular box. If there is a follow-up question about dimension of the rectangular box, then it will be, this is, remember, 24 minus 2s. So it's 20 by 2 by, this is 5, correct? So if you check now, 20 cm, 5 cm, and 2 cm, the volume will be, okay, the length 20 cm, the width 5 cm, and the height, which is 2 cm. Volume, the largest volume is 200 cubic centimeter. Cubic. Is it centimeter in our problem? Okay. Okay. So, 200 cubic centimeters. Problem number 9. Problem number 9. If one side of a rectangular field is to have a river as a natural boundary, find the dimension. So this time it's asking for dimension of the largest rectangular field that can be enclosed using, okay, 240 meters of fencing material. Okay, so how many sides of the rectangular field will be enclosed using this amount of material? 3 sides only, because one side is along the river and that will be its natural boundary. So what are we going to enclose then? This side of the rectangular field, this side, and this side. Okay? And this in fact is the perimeter minus one side. Okay? So what equation can we set up out of this? So for problem number, let me take a snapshot or a screenshot so that we will have a guide. Okay, this one. I'll delete this now. Okay, ito yun. So what are given in the problem? Given amount of fencing material, which is 240 meters. Okay? Yan, 240 meters of fencing material. Fence to cover, okay, to enclose this side, and this side of the rectangular field. So what is 244? To enclose for fencing. Enclose this, let it be y. Let this be y. Since rectangular, this side should be equal. So if this is y, then the other should be y. And let this be x. So the length is x. The length is x. And the width is y. Okay. By amount of material, 240 meters is equal to, okay, x plus 2y. May we disregard the unit first? We will only make use of the unit, okay, after we shall have found the dimensions. This problem asked for dimensions. That's why we made use of two variables, x and y. Now, what quantity is to be maximized? Largest rectangular field. Okay, which means, okay, this one requires maximum. Okay, what quantity is to be maximized? Area. The largest, okay, the largest rectangular field. So, A is the quantity, area. Area is to be maximized. A while ago, in our previous problem, the quantity to be maximized is volume. This time, area is to be maximized. And what is area equal to? Area is equal to length times width, yes? But we have represented the length as x and the width as y, so area is equal to xy. But remember from the steps that we have enumerated, we said that as much as possible, we have to express the quantity to be minimized or maximized in terms of one variable only. So we can either replace or express x in terms of y or y in terms of x. From where? From the given. Okay? And relationship between and among the unknowns and knowns. We have one equation that we were able to set up a while ago, which gives the fencing material perimeter. So from here, I could express y in terms of x. Okay, so if I may change or I may do transformation from 240 is equal to x plus 2y, then 240 minus x is equal to 2y, which means that y will be 240, okay, y is equal to 240 minus x over 2. Okay, that is our y. So, in our area formula, I'm now going to express y in terms of x using this equation. Okay, from here. So, times, I'm not done yet. 240 minus x all over 2. Or we can express this as, okay, 1/2 of, okay, 240x minus x squared. Okay? Or simply 120x minus 1/2 x squared. Now we take a prime. So after expressing the quantity to be maximized in terms of a single variable, of one variable only, we now proceed to differentiating that quantity or that formula or equation. We now differentiate. Okay, we now differentiate. So we have expressed a in terms of x. So a prime will now be 120 minus, okay, 120 minus x. Okay, 120 minus x. Okay, so a prime, or after differentiating, we now, okay, yx, because this and 2 will cancel out, leaving x. Okay, how about 1/2? Oh, we failed to include 1/2. Oh, tama, it's okay. From here, okay, 240x divided by 2, 120x, and then x squared over 2, or 1/2 x. Okay, so what will this be? X is equal to 140, x is equal to, so after differentiating, we equate the first derivative to 0, equate the first derivative to 0 to find the critical number. So from the previous, we have 120 minus x equals 0. 120 is equal to x. Okay, what is x? X is the length. So x here, we were able to find x already. X is equal to 120. How about y? So 120 centimeters, 120 centimeter is the length. How about the width? Okay, solve for y. Okay? Using the equation that we have arrived at last time here, 240 minus x over 2 is equal to y. Or from here. Okay, from here. Okay, from the given. 240 plus, or equal to rather, 240 is equal to 2y plus x. Okay, 240 is equal to 2y plus 120. Okay, x is 120. So, 240 minus 120 is equal to 2y. So, 120 equals 2y. Y is equal to 60. Okay, so the width is 60 cm. Okay, the width is 60 centimeters. If we check, so 120 cm plus 60 cm plus 60 cm is equal to, correct, 240 cm. cm? Was it cm? Checking the given, it's meters. Okay, 240 meters. This is supposed to be meters. meters, 240 meters. Okay, so we were able to find the dimension. So our answers are length, because the problem asks for dimension, is 120 meters, 120 meters, and the width is 60 meters. Okay, last problem, number 10. Find the dimensions of an open-top cylindrical can that can be constructed with the least amount of material. Let me underscore, least amount of material, which can hold a volume of 30 cubic meters. Okay, 30 cubic meters. So let's find the dimensions. This problem also calls for dimension. So the problem calls for dimension of the cylinder. That would contain a volume of 30 cubic meters. Okay, 30 cubic meters. Open top. Open top. Top is open. And least amount of material. Okay, so from here now, we can now set up our equation. So these are the given. The volume is 30 cubic meters. The top should be open. And the quantity to be minimized this time is amount of material, M. So when we speak of volume of a cylinder, volume is equal to the area of the base times the height. And you know for a fact that the base of a cylinder is a circle. And area of a circle is V is equal to pi r squared. And the height is h. Okay, pi r squared. And the volume given is 30.